In this video, I will talk about the divergence. And I have here the definition of the del operator, and here on this line I have my function f that is really a vector field. So this function f is a vector, and you can see I have an x component, a y component, and a z component. The way that I can calculate the divergence is the following. What we define as the divergence is the dot product between the del operator and this vector function. Now, when I had the gradient, I want to remind you the difference with a gradient is that when I found the gradient, my function was a scalar function, and I was just applying the del operator to the function. Here, for the divergence, I have two vectors, the del operator and the function f, and I am finding the dot product. Okay, the divergence is a dot product between two vectors. Now, we know that the dot product between two vectors should give us a scalar. So I need to, I am expecting that I will get a scalar when I find this dot product. Now, I know a little bit of background. X hat dot x hat, because those are unit vectors, I will get 1. But if I take the dot product with x hat and y hat, because those are perpendicular to each other, I get a 0, and similarly x hat dot z hat, I will also get a 0. So the only term that survives when I find the dot product, the x hat dot x hat should give me 1, and then what I get from the x components is this. Okay, x hat dot x hat will give me 1, and the partial derivative of the x component of the function with respect to x. And similarly, plus the same thing in the z with the z component. So this is the divergence. Now, this, just by looking at it does appear, and it is somewhat abstract. What does this really mean? I'm gonna try to explain that. Let's say that I'm gonna show you a 2D function. I could do more, but it's just gonna take me more time. Okay, so you can think that what I have here, this is my function f. Now I will constrain myself to 2 dimensions, x and y. Okay, I cannot really work with 3 dimensions, but what I will explain here with in 2 dimensions, you can generalize it to the z axis as well. Now, I'm gonna show you what the first, let's say that this is the x and this is the y, okay, and the z is going out of the page. Now, I want to see what this is, what the first term is telling me, and I will write it here. So this is what I want to think about. The fact the partial derivative of f of x with respect to x. What does that mean? That it means I have to think about making a small change in x. Okay, this is what this is telling me. And when I make a small change in x, I need to evaluate if the x component is changing and by how much. So I need to find the change of the x component of the function. Now, this is one way to look at it. If, let's say, I am here and I'm making a small change in x and I go from here to here. Okay, this is my change in x. Now I'm gonna think at this vector and this vector first. What are the x components? Here I have a small x component, here I have a larger x component. Did the x component of my function change? Yes, it did. How did it change? If I went from here, if this is my initial and this is the final, I ended up here, as I go to the right, the x component of the function increases. So the change in f of x is a positive number. Even so that was one. Even if you look at these vectors, you go from here to here, you think about the x component of the vector on the x-axis. As you go from the initial to the final, yes, there is a change. Anywhere you look at it, there will be a change as you go from a smaller x to a larger x. You will find that the change in the x component of the function is a positive number. What does that tell me? It tells me that this is it tells me that the partial derivative of f of x with respect to x is a positive number. Now that was only for the first term, okay? I also have to think about the second one. Because remember, the divergence is the addition, the sum of those three terms. So what I'm gonna do now, what does this partial derivative tell me? It tells me that I have to think about making a change in y. And then when I make a change in y, I have to evaluate how the y component of my function changes. I need to find the change of the y component of the function. Now this is my y-axis, so what I'm gonna do, I'm gonna think, okay, let's say I start here. Okay, this is my initial point, and let's say I go there, that's the final. So I'm making a change in the y. I go from here to here. Now, just look at these two vectors, even this one too. The y component of my function, when you increase the y, also increases. Okay, here I have a small y component, a larger y component, and even larger y component. This means that as I make a positive change in the y, as I have a positive change in y, the y component of the function is also positive. What that means is that this term, the second one, is also a positive number. And if you think that the same, if you want project, if you visualize that the same thing takes place on the z-axis, then the last term will also be a positive number. And at the end, if you add three positive numbers, in this example, you get that the divergence of the function f will be, okay, I'm not using any specific function here. The only thing that I know is that this needs to be a positive number for that particular example. Now this, and you know, the name, the notation, the name that we use for this particular dot product, divergence, it shows you the fact that this vector function does diverge from, in this case, from the origin. It goes, this vector function diverges away from that point. Now I can do one more. I can show you. Let's do, okay, I can do it here. I try to make those being or look like they are the same distance. So this is now my vector function, and I'm gonna keep the same x and y axis. Okay, I'm gonna start with the y this time. I'm gonna start from here. This is the initial, and then I go here. That's the final. I'm making a positive change in the y. I can see, as previously as before, I can see that the y component of the function changes, it increases. So I have for a positive delta y, I have a positive change in the y component of the force. Now what this is telling me is that for this particular vector function, the partial derivative of fy with respect to y, I know that this is a positive number. Now I will also think about the first term, the partial of f of x with respect to x. Now I'm gonna make a change in the x direction. So let's say I start from here and I go there. That's my final, that's my initial. I am making a positive change in x, and what do I see? What is the change of the x component of my vector function? I don't see a change. Whatever I have here, I have exactly the same thing, and in fact the x component is exactly 0. And not only it's 0, but it's not really changing. So this means the change of f of x is 0 for a positive change in x, and what that tells me is that this first term is exactly 0. Now, what do you get if you add the two? Well, you have a positive number and 0 of the divergence. In this case, you will find it to be a positive number. But you can see that the function here does diverge from a point. Okay, it does diverge, and the fact that it's increasing the further you go, that's the indication that the divergence is a positive number. So that is how we need to think about the divergence. This is the definition, and that's how that's the, if you want, the geometrical interpretation of the concept of divergence.